Hello everyone, and welcome to today's chem lesson. Today, we're going to talk more about equilibria, specifically how we can take an equilibrium, right, one where the rate of the forward reaction is equal to the rate of the reverse reaction, and shift that equilibrium, cause one side to be more productive than the other, right, essentially breaking the equilibrium and allowing it to reset itself. The person who did all the research on this was a man named LeChatelier, and he studied these equilibria. He put pressure, he caused shifts to these equilibrium, he caused them to change, and he studied what happened before and after, and what he did, and how it affected the equilibrium. He found three different things that caused an equilibrium to shift that we're going to talk about. And those things were concentration, temperature, and pressure. But before we are able to really talk about what happens, we need to define this word. We need to talk more about the idea of a shift. When we look at an equilibrium, right, if I take this equilibrium of A plus B going back and forth between this compound AB, this by itself is a reversible reaction. If I want to call it an equilibrium, that means that the rate of the forward reaction, A plus B making compound AB, and the rate of the reverse reaction, AB breaking down to make the elements A and B, need to be the same. Every 10 seconds, 1 mole of AB is produced. Every 10 seconds, 1 mole of AB decomposes into A and B. This equilibrium exists only at a very specific set of circumstances. I set this up in a way that allows those rates to be equal. If I change the temperature, the pressure, the concentration of any of these pieces, I am going to cause one side to become more dominant. Either the creation of AB will speed up, or the breaking down, the decomposition of AB will speed up. And it will not be in equilibrium anymore. It will be unbalanced. The rate of one side will be faster than the rate of the other. If you do a shift correctly, it is a temporary change. Just like if I reach out and I push you a little bit to the left, you will rebalance yourself by leaning more to the right. Right? Your body will rebalance itself with a small enough push. Now, if I take my full force, the full power of my many muscles to shove you as hard as I can, you're going to fall over. There's no amount of balance your body can fix that with. The idea of a shift is it's a little push causing one side to speed up, right? One side to move faster than the other, or to slow down one side and allow the equilibrium to rebalance itself, to regain that composure, to make those rates of forward and reverse equal again. Let's look at this through some examples. The first is changing concentration. If you increase the concentration of a piece of an equilibrium, the odds of that substance colliding and doing the reaction that it's involved with gets higher. Right? We know that in order for a reaction to happen, the involved pieces need to collide at the right angle with the right amount of energy. And we talked about adding more of one piece will allow that reaction to speed up. So let's look. Here we have the Haber process, the creation of ammonia. It exists at equilibrium where N2 and 3 H2s collide together to make 2 ammonia molecules, and 2 ammonia molecules collide with each other and break down to make H2 and N2. This equilibrium exists in some sort of closed container. If I increase the concentration of N2, if I, with a little syringe or something, inject a little bit more N2 into this bottle, what is that going to do? That's going to increase the concentration of N2. That's going to be the push. That's going to be the stress that I cause on this equilibrium. Right? That's me giving you a little shove. And how are you going to right yourself? How is this equilibrium going to fix itself? If I've added more N2, that means the forward reaction is going to speed up. For a small period of time, N2 and H2 are going to make NH3 faster than the NH3 breaks down. Right? This means we're going to shift to the right. Right? The reaction of the forward reaction, right? The reaction rate of the forward reaction has increased because I added more N2. By adding more N2, these collisions are going to happen more often than these collisions. So we'll see something like this will happen once every 2 seconds, where this happens once every 3 seconds. So it happens faster, but eventually it will slow back down and these will re-establish an equilibrium. As a result of this shift, as a result of me adding more N2, I'm going to make more NH3, and I'm going to use up more N2 and H2. Because for a while, the forward reaction happened more than the reverse, I'm going to get a buildup of NH3 and a decrease in N2 and H2. The second change is a change in temperature. Remember, when you have delta H as part of a reaction, you can include it as a reactant or a product, depending on the sign of delta H. Take a second, refresh your memory, see if you can accurately put this delta H in this equilibrium correctly. Does it go on the left? Does it go on the right? If you rewrite this equilibrium, the delta H, a negative delta H, means exothermic, means energy is produced, means energy is a product, means energy goes on the right side. So we put the energy on the right side. And once the energy is in the equation, we can treat it just like we treat any other part of the equation. If you add more energy, if you increase the temperature, you're adding something on this side. That means that these collisions are going to happen more often, meaning you're going to speed up the reverse reaction. You're going to shift this reaction to the left. If you decrease temperature, if you take away something, you're going to cause the reaction to slow down, right? If I take away some of the temperature, if I take away some of the energy, the reverse reaction is going to happen less than the forward reaction. And the forward reaction is going to speed up. We're actually going to shift towards the right side. every time you make a change, every time you put stress on an equilibrium, the equilibrium will shift in order to right that change, in order to fix whatever you have messed up. If you add temperature, if you add something on the right side of the equation, the equilibrium will shift to the other side to relieve that stress that you have put on it. If you take away something from the right side of the equation, the equilibrium will shift towards that side, towards the right side, to try to fix the hole that you have created by taking out a piece. It's all about making sure that the equilibrium has the chance to right itself, to fix itself. Again, if you do too big of a shift, if you drop the temperature to 0 degrees, you're going to not just stop the equilibrium from fixing itself, you're going to stop this reaction from being a double-sided reaction. Right? If I take away all of the H2O, the forward reaction can't happen anymore. We're not going to have any movement from left to right. It'll all be from right to left. We take away the double-sided arrow and end up with a single-sided arrow. Right? These have to be small changes. A small change can be fixed. A big change cannot be fixed. Right? You're trying to give the equilibrium a little push, not knock it to the ground. The last of these three shifts, the last of these three changes that cause shifts, is a change in pressure. And a change in pressure is a little bit different from the other two because a change in pressure only looks at the moles of gas on either side. If you increase the pressure, if you take the container and shrink it down and squeeze it down, you are going to force the equilibrium to move towards the side that takes up less space. Right? If you squeeze and squeeze and squeeze and condense that equilibrium down, you are going to force the reaction of the bigger thing to become the smaller thing. When we're looking at the size or the amount of space something takes up, we're really looking at how much gas there is. There's not much you can do to compress a solid. There's not much you can do to compress a liquid, but you can absolutely compress a gas. So if you increase the pressure on an equilibrium, it will shift towards the side with fewer moles of gas. If I take this equilibrium and I increase the pressure, I am going to shift to the right. Why? Because the left side has a total of 4 moles of gas, while the right side has a total of 2 moles of gas. By compressing this equilibrium, these things are going to collide much more often, causing the left to right, the forward reaction, to speed up. Eventually, a new balance will be reached, right? A new equilibrium will be reached, but not until things have changed here. Not until we have increased the amount of NH3 and decreased the amount of N2 and H2. Now, I understand that this is actually one of the tougher concepts that we have to talk about. So, what I have for us is a fun graph. Everybody loves... Actually, this isn't even a graph. It's a table. We love tables. Tables are great. Alright, what we're going to do here is we are going to label If this is the stress that you cause to the equilibrium, white was a terrible color here. Let's go purple, right? If this is the stress that you cause the equilibrium, is it going to cause the equilibrium to shift to the right or shift to the left in order to fix it? Is it going to cause the amount of NH3 to go up or to go down? Is it going to cause the amount of N2 to go up or go down? Is it going to cause the amount of H2 to go up or go down? Right? And we're looking at these after we have reestablished equilibrium. Right? Let's do this first one together. And then I'm going to give you some time to look at these. If I increase the amount of H2, if I have this in a container and I throw in extra H2, H2 is here on the left side of the equilibrium. By adding more H2, it will cause the N2 and the H2 to collide more frequently. It does not affect the NH3, but it will cause the left side of the reaction to collide more frequently. It will mean the forward reaction speeds up. We're going to shift to the right. So that means temporarily, the left to right, the forward reaction, will be happening more frequently than the right to left, than the reverse reaction. Over time, the forward reaction will then start to slow down a little bit, the reverse reaction will start to speed up a little bit, and they will re-establish equilibrium. The rates will balance out. And when the dust is settled, after everything is said and done, after we have finished shifting and re-established our equilibrium, we will have more NH3 than we started with, because we will have gone from left to right more frequently than we went from right to left, so the NH3 will increase. The N2 and the H2, we will have used those up. These are going to decrease. Because just like I said, we were using them to make more NH3. We're shifting that balance, we're throwing off the balance, we're changing the amount of each of these things. Then we reestablish equilibrium. And with these new concentrations, whatever they are, we have now hit a point where the forward and the reverse are back at the same rate. Pause the video here and try to fill in the rest of this table. And when you unpause the video, right, I'm going to wait a couple of seconds. When you unpause the video, I am going to go through these answers. And we're going to do it for two more. I've got two more of these charts for us to look at. Welcome back. Right, let's take a look at our answers here. Overall, these should be the directions that our arrows are pointing. The shifts to the left or the right, the concentration, the amount of the NH3, the NN2, and the H2 going up or down. And there's a pattern we're going to notice here, and the pattern I'm going to point out to us, but let's talk through all of these. We already talked through the first one about increasing the amount of H2. What if I decrease the amount of NH3? What if I took away NH3? What is that going to do? It is going to slow down the reverse reaction. It's going to mean that these are going to collide and break down less frequently than they did before. That means that the forward reaction is going to be faster than the reverse. It means that we are going to shift to the right side. After we have shifted, right, as a result of us doing this decrease in NH3, the concentration of NH3 will be brought up, right? It's going to increase because we're making it faster than it breaks down. the amount of N2 and H2 are both going to decrease because we are using them up faster than the NH3 produces them. Right? We're going more left to right and less right to left. If we decrease the pressure, we open up this container, we expand this container, and we allow everything to kind of stretch and spread out. By allowing that, we allow the side with more moles of gas to be prominent. Right? That's this side with 4 total moles of gas. We're going to shift to the left side. We're going to allow everything to kind of spread out and stretch. These are going to collide more frequently. These are going to be able to take up more space. As a result of this shift, the NH3 concentration is going to go down. We're going to use it up faster than it gets made. The N2 and the H2 are going to go up. We're making them faster than they combine. Increasing the amount of NH3 by putting more NH3 into this container, we are making it so that the NH3 collides more frequently. We're speeding up the reverse reaction. So we're going to shift towards the left. We're going to make N2 and H2 faster than N2 and H2 combine to produce NH3. Decreasing the N2 concentration, right? Taking away some of the N2 means that it's harder for the N2 and the H2 to collide. So we're actually slowing down the forward reaction, allowing the reverse reaction to be faster. This is going to mean that we make more N2 and H2, make less NH3, right? The NH3 is getting used up. The N2 and the H2 are being produced more quickly than they combine because we are shifting to the left. Increasing pressure is another look back, right? If we increase the pressure, we are going to speed up the forward reaction, right? By compressing all these things together, these are going to collide more often. We're going to produce NH3 faster than the NH3 breaks down. So we're going to shift to the right. The amount of NH3 is going to increase. We're going to make it faster than it breaks down. The amount of N2 and H2 are going to decrease. We're going to use them up faster than they get produced. Let's look at another graph here, another chart, another table. New reaction. This one, I'm giving you the delta H. This is a positive delta H. It tells us that this is an endothermic reaction. It means energy is a reactant. Right? We need energy in order to have this reaction happen. It means that energy goes on the left side. So we're going to put the 33 kilojoules on this side. Now again, pause the video here and see if you can predict the shifts and the change of our concentrations here. Alright, let's take a look at our answers for this chart. So we're going to go through them one at a time. First, if I increase the temperature, right, we said that the energy went on this side of the reaction, right, it went on the left side. So if I increase the temperature, I'm adding something on the left side. I'm going to cause this collision to happen more frequently. I'm going to cause the forward reaction to speed up. The reverse reaction stays exactly the way it was. By speeding up the forward reaction, I'm going to make more N2, make more O2, and use up my NO2. So decreasing NO2, increasing N2, increasing O2. If I decrease the concentration of NO2, if I take away some of the NO2, I am slowing down the forward reaction. It will not go as quickly as it was going before because it's harder now for a successful collision to happen here. The reverse reaction is now going to be the one that's faster. Not because I made it faster, but because I slowed down the forward reaction. I'm going to shift to the left. I'm going to make more NO2 because I'm making it faster than it breaks down. I'm going to decrease the concentration of N2 and O2 because I am using them up to make more NO2 faster than they are produced. Now, for this third one, I put no change. There's no change in the equilibrium if I increase the pressure here. Or if I decrease the pressure, right? It doesn't matter increase or decrease here. Now, why is that? The reason for that is because there are 2 moles of gas on the right side of the equation, and there are also 2 moles of gas on the left side of the equation. Since these numbers are equal, if I compress or expand this equilibrium, if I take the container it's in and compress it or expand it, it's not actually going to change anything. There is no side of the equation with more or less moles of gas. They have the same amount. So pressure doesn't do anything here. Decreasing the N2 concentration means I am slowing down the rate of the reverse reaction, which allows the forward reaction to be the dominant, faster reaction. So I'm going to shift to the right side. I'm going to make N2 and O2 faster than they combine to make NO2. I'm going to use up my NO2 because I'm breaking it down faster than the N2 and the O2 combine. If I increase the concentration of the oxygen, if I add more oxygen, then the collisions between the N2 and the O2 are going to increase. The rate of the reverse reaction is going to speed up. I'm going to create more NO2. I'm going to create NO2 faster than it breaks down. I'm going to use up my N2 and my O2 because those collisions are happening more frequently to make the NO2 than the NO2 colliding with itself and breaking down to make the N2 and the O2. If I decrease the temperature, if I take away something from the left side, the collisions that happen on the left side are going to be less frequent. So I'm slowing down the forward reaction, allowing the reverse reaction to be the dominant one, meaning I make NO2 faster than it breaks down, and I use up my N2 and my O2 faster than they are produced. Now, if we look at our answer choices here, if we look at each row of this chart, there are only 2 types of shifts. A shift to the right makes the things on the right side of the arrow increase, and the things on the left side of the arrow decrease. Every time. Look at both of these shifts to the right. Both of them have NO2 going down. Both of them have N2 going up. Both of them have O2 going up. Because a shift to the right means that the forward reaction is happening faster than the reverse. We are using up our NO2 faster than we make it. We are making N2 and O2 faster than they are being used up. If we look at the other three shifts, all of those shifts to the right side, to the left side. If we shift to the left, we are increasing each of our things on the left, and we are decreasing each of the things on the right. For the same set of reasons, right? We are making the reverse reaction faster. That means we are using up N2 and O2 faster than we create it. We are creating NO2 faster than it breaks down. Let's look at just one more. I have one more table for us. It's right here. Again, pause the video here. And then we're going to go over these problems in about 10 seconds. Our answers here look a little bit like this. Actually, they look exactly like this. First, let's put our delta H into the equation, right? It's a negative delta H, means an exothermic reaction, means energy is a product. Put it on the right side of the arrow. Increasing H2 means we are adding something on the left side. We are allowing the left side to collide more frequently than the right side. We are speeding up the forward reaction. Increase in HCl, decrease in H2 and Cl2. We use those up faster than we make them. We make HCl faster than it breaks down. Increasing the temperature, right? Energy is on the right side of the arrow, so that means that it's going to cause the reverse reaction to speed up. We shift to the left. We make H2 and Cl2 faster than they combine, and we use up HCl faster than it is produced. Again, we have a situation where there are 2 moles of gas on both sides. And so, pressure has no effect on this equilibrium. It speeds up both sides equally. There is no overall change to the equilibrium here. Then, we look at decreasing the HCl concentration. If I take away some of the HCl, that means I slow down the reverse reaction. That means that the forward reaction is faster. That means I'm going to make HCl faster than it breaks down. And I'm going to use up H2 and Cl2 faster than they get made. Decreasing the Cl2 concentration has the opposite effect, right? If I take some of this out, then these collisions happen less frequently, then this forward reaction slows down, and the reverse reaction is the one that's faster. I'm going to decrease the amount of HCl that I have. I'm breaking it down faster than it gets created. And my H2 and Cl2 are going to go up. I am making them faster than they are combining. Lastly, if I decrease temperature, if I take away some energy, it means that I'm slowing down the reverse reaction, allowing the forward reaction to be faster. That means I make HCl faster than it breaks down. It means I use my H2 and my Cl2 faster than they get produced. Every shift, every time we're looking at shifting an equilibrium, we are either speeding up one side or slowing down one side. The question you need to ask yourself to determine what side we are shifting towards is which side of the equilibrium, forward or reverse, is the faster side. If the forward reaction is faster, we are shifting to the right side. We are making more products than reactants. If the reverse reaction is faster, we are shifting to the left. And we are making more reactants than products, right? We are making reactants faster than we create the products. And that is LeChatelier's principle. And that's really all there is for kinetics and equilibrium. That's the end of this unit. So I'm going to sign off here, and I'm going to wish each of you a fantastic day.